In this lecture, we're going to talk about model validation and testing. So when you create a model, you need to validate and test it, and it's very important to follow the right procedure. So this is going to be different depending on whether you have built a statistics model or a machine learning model. And we have different metrics to measure the performance of classification and regression models. So here's an overview of what we're going to see. So in statistics, what we mainly care about is the validation of the model assumptions. So we care about testing for the goodness of it, we care about comparing between different models, we care about the goodness of fit as in how well does the model predict the data, and in machine learning we care mainly about the generalization of the model. That is, how well does a model that has been trained on a set of data, how well does it perform in the real world when we use it on previously unseen instances? How good are its predictions? So let's start with some basic concepts. Occam's razor is a very important tool in our toolbox, which refers to a heuristic that basically the heuristic says that simpler explanations should be preferred over more complex ones. So this means that if you have two models and they perform the same, you should try to use the simplest one. You should make as few assumptions as possible around a problem, and you should eliminate those assumptions that make no difference in the observable predictions. The issue we have with machine learning is that quite often accuracy and simplicity are in conflict. So let's see this example here. Which one would be better? So we have again this example of email length and the new recipients and trying to classify spam from ham. And we have a simple model that makes two errors. So this model is simple because it's only a straight line, and then we have a more complicated model that has 0 errors. So the answer is that the simpler model would be preferred in this case. The reason being that more complicated models tend to overfit. They tend to not be able to discern between the noise and the signal, and to use noisy patterns as signals. So whereas the performance of the training set will be perfect, when time comes to use this on test data, then the performance will be suboptimal. So some things we need to care about when we build our models. In machine learning, something we care about is overfitting. That is, our model not generalizing well to new data. Another concern, which is a concern for both machine learning and statistical models, is underfitting. This means that our model is not really suited for the problem task, so it's not really performing well. And another thing that we care about is interpretability. That is, how easy is it to understand what the model is doing? So Wolpert in 2001 came up with an off-freelance theorem. This says that for any two learning algorithms, there are just as many situations in which algorithm 1 is superior to algorithm 2 and vice versa, according to any measures of superiority. So according to Wolpert, when we try to choose an algorithm, we're a little bit doomed because there's no notion basically of an algorithm that is the best. So what Wolpert is saying that one algorithm might be good in problems A, B, and C, and then algorithm 2 will be good in some other problems. So there's no guarantee as to which algorithm is the best one. However, even though Wolpert's theorem is true, in practice we don't care too much about it. The reason being that practitioners are mostly concerned with choosing the most appropriate algorithm for a problem at hand. And for specific domains and problems, we have some a priori knowledge, we know what the data distribution looks like, we know the complexity of the problem, etc. So even if across all possible problems, we can't get any guarantees of which algorithm is the best, in each domain there are certain regularities that make some algorithms better than others on average. So again, this slide summarizes what I just mentioned, that as a practitioner, what you should care about is identifying the best classifier for each problem. So something else important to note is that what the no-freelance theorem tells us, and actually experience proves the same, is that simple classifiers are not necessarily worse than complex classifiers. It really depends on the problems. So in some problems, we might want to have simpler classifiers or classifiers with very high bias. Whereas in complicated problems, maybe we need to use more complicated classifiers. But again, it's not only just about whether a classifier is simple or complex, because it's also about the specific type of the classifier. So maybe random forests will perform very well on a problem where deep neural networks will fail, but both of these classifiers are quite complex compared to logistic regression, for example. That's why it's important to be aware of all the different techniques that are out there and then be able to find the best algorithm for each situation.